नमस्कार, मैं आनंद कुमार खत्री। आज के हमारे लेक्चर का विषय है एटमॉस्फेयर, पार्ट थर्ड, ट्रोपोस्फियर। The lowest portion of the atmosphere in the troposphere, a layer where temperature generally decreases with height. This layer contains most of Earth's cloud and is the location where weather primarily occurs. This is the diagrammatic or layer wise presentation in which you can see the layer of Earth's atmosphere with a yellow line showing the air temperature. Planetary boundary layer. The lower level of the troposphere are usually strongly influenced by Earth's surface. This sublayer, known as the planetary boundary layer, is that region of the atmosphere in which the surface influences temperature, moisture, and wind velocity through the turbulent transfer of mass. As a result of surface friction, winds in the planetary boundary layer are usually weaker than above and tend to blow towards areas of low pressure. For this reason, the planetary boundary layer has also been called as Ekman layer for Swedish oceanographer Wagen Wilfred Ekman, a pioneer in the study of the behavior of wind-driven ocean currents. Under clear, sunny skies over land, the planetary boundary layer tends to be relatively deep as a result of the heating of the ground by the sun and as the resultant generation of convective turbulence. During the summer, the planetary boundary layer can reach highest of 1 to 1.5 kilometers, 0.6 to 1 mile above the land surface, for example, in the humid eastern United States, and up to 5 kilometers, 3 miles in the southern western desert. Under these conditions, when unsaturated air rises and expands, the temperature decreases at the dry adiabatic lapse rate 9.8 degree per centigrade per kilometer or roughly 23 degree Fahrenheit per mile throughout most of the boundary layer. Near Earth's heating surface, air temperature decreases super adiabatically at a lapse rate greater than the dry adiabatic lapse rate. In contrast, during clear, calm night, turbulence tends to cease and radiational cooling. Net loss of heat from the surface results in an air temperature that increases with height above the surface. When the rate of temperature decreases with height exceeds the adiabatic lapse rate for a region of the atmosphere, turbulence is generated. This is due to the convective overturn of the air as the warmer lower level air rises and mixes with the cooler air aloft. In this situation, since the environmental lapse rate is greater than the adiabatic lapse rate and sending parcel of air remains warmer than the surrounding ambient air, even though the parcel is both cooling and expanding. Evidence of this overturn is produced in the form of bubbles or eddies of warmer air. The larger bubbles often have sufficient buoyant energy to penetrate the top of the boundary layer. The subsequent rapid air displacement brings air from aloft into the boundary layer, thereby deepening the layer. Under these conditions of the atmospheric instability, the air aloft cools according to the environmental lapse rate faster than the rising air in cooling at the adiabatic lapse rate. The air above the boundary layer replaces the rising air and undergoes compressional warming as it descends. As a result, this enter, entrant air heats the boundary layer. The ability of the convective bubbles to break through the top of the boundary layer depends on the environmental lapse rate aloft. The upward movement of the penetrative bubbles will decrease rapidly if the parts quickly becomes cooler than the ambient environment that surround it. In this situation, the air parcel will become less buoyant with additional ascents. The height that the boundary layer attains on a sunny day, therefore, is strongly influenced by the intensity of surface heating and the environmental lapse rate just above the boundary layer. The more rapidly a rising turbulent bubble cools above the boundary layer relative to the surrounding air, the lower the chance that subsequent turbulent bubbles will penetrate far above the boundary layer. The top of the daytime boundary layer is referred to as the mixed layer inversion. On clear, calm night, radiational cooling results in a temperature increase with height. In this situation, known as a nocturnal inversion, turbulence is suppressed by the strong thermal stratification. Thermally stable conditions occur when warmer air overlies cooler, denser air. Over flat terrain, a nearly laminar wind flow, a pattern where winds from an upper layer easily slide past winds from a lower layer can result. The depth of the radiationally cooler air layer of air depends on a variety of factors such as the moisture contents of the air, soil and vegetation characteristics, and terrain configuration. In a desert environment, for instance, the nocturnal inversion tends to be found at greater heights than in a more humid environment. The inversion is more humid environment occurs at a lower altitude because more long wave radiation emitted by the surface is absorbed by numerous available water molecules and remitted back towards the surface. As a result, the lower level of the troposphere are prevented from cooling rapidly. If the air is moist and sufficient near surface, cooling occur, water vapor will condense into what is called radiation fog. Wind generated turbulence. During windy conditions, the mechanical production of turbulence becomes important. Turbulence eddies produced by wind shear tends to be smaller in size than the turbulence bubbles produced by the rapid convection of buoyant air. Within a few tens of meters of the surface during windy conditions, the wind speed increases dramatically with height. If the winds are sufficiently strong, the turbulence generated by wind shear can overshadow the resistance of layered thermally stable air. In general, there tends to be a little turbulence above the boundary layer in the troposphere. Even so, there are two notable exceptions. First, turbulence is produced near jet streams where large velocity shears exist both within and adjacent to cumuliform clouds. In these locations, buoyant turbulence occurs as a result of the release of latent heat. Second, pockets of buoyant turbulence may be found at and just above cloud tops. In these locations, the traditional cooling of the clouds destabilizes pockets of the air and makes them more buoyant. Clear air turbulence (CAT) is frequently reported when aircraft fly near or one of these regions of turbulence generation. The top of the troposphere, called the tropopause, corresponds to the level in which the pattern of decreasing temperature with height ceases. It is replaced by a layer that is essentially isothermal of equal temperature in the tropics and subtropics. The tropopause is high, often reaching to about 18 km 11 miles as a result of vigorous vertical mixing of the lower atmosphere by thunderstorms. In polar regions where such deep atmospheric turbulence is much less frequent, the tropopause is often as low as 8 km 5 miles. Temperature of the tropopause ranges from as low as minus 80 degree centigrade in the tropics to minus 50 degrees centigrade in polar region. Cloud formation within the troposphere. The region above the planetary boundary layer is commonly known as the free atmosphere. Winds at the volume are not directly retarded by surface frictions. Clouds occur most frequently in this portion of the troposphere, though fog and clouds that impinge or develop over elevated terrain often occur at lower level. This is the cloud formation at various heights. There are two basic types of clouds: cumuliforms and stratiforms. Both cloud types develop when clear air ascends, cooling adiabatically as it expands until either water begins to condense or deposition occurs. Water undergoes a change of state from gas to liquid under these conditions because cooler air can hold less water vapor than warmer air. For example, air at 20 degrees centigrade can contain almost 4 times as much water vapor as at 0 degrees centigrade before saturation takes place and water vapor condenses into liquid droplets. Stratiform clouds occurs as saturated air is mechanically forced upward and remains colder than the surrounding clear air at the same height. In the lower troposphere, such clouds are called stratus. Evacuation fog is a stratus cloud with a base lying at Earth's surface. In the middle troposphere, stratiform clouds are known as altostratus. In the upper troposphere, the terms cirrostratus and cirrus are used. The cirrus cloud type refer to thin, often wispy, cirrostratus clouds. Stratiform clouds that both extend through a large fractions of the troposphere and precipitates are called nimbostratus. This is the cirrus fibratus clouds are high clouds that are nearly straight or irregularly curved. They appear as fine white filaments and are generally distinct from one. Cumuliform clouds occur when saturated air is turbulent. Such clouds, with their bubbly terrated shapes, exhibits the small scale up and down behavior of air in the turbulent planetary boundary layer. Often such clouds are seen with bases at or near the top of the boundary layer as turbulent eddies generated near Earth's surface reach high enough for condensation to occur. This is the cumulus clouds, flattened clouds characterized by only a small vertical extent. Cumuliform clouds will form in the free atmosphere if a parcel of air upon saturation is warmer than the surrounding ambient atmosphere. Since this air parcel is warmer than its surrounding, it will accelerate upward, creating the saturated turbulent bubble characteristics of a cumuliform clouds. Cumuliform clouds which reach no higher than the lower troposphere are known as cumulus when they are randomly distributed, and as stratocumulus when they are organized into lines. Cumulus congestus clouds extends into the middle troposphere, while deep precipitating cumuliform clouds that extends throughout the troposphere are called cumulonimbus. Cumulonimbus clouds are also called thunderstorms since they usually having lightning and thunder associated with them. Cumulonimbus clouds develop from humulus and cumulus congestus clouds. Thanks.